Number 5 is a question on material from the first exam, and it's about aromaticity. So first we have to define what does it, first of all, the question asks, which of these 6 structures is not aromatic? So let's start by defining what aromaticity is. To be an aromatic ring, you need to go through this checklist, and all 4 of these must be true for you to be aromatic. 1, you must be a ring. Well, looking at all of our structures, they're all rings, so that's going to be a check, so that can't be what we're ruling out. 2, they must be planar. Now, for something to be planar, generally you're not going to have to deal with this in a question, so you can usually assume if it's a ring and it's fully conjugated, then it's planar. But if you see, like, in the ring there is maybe a wedge or a dash, that would imply it's no longer planar, and that's how you'd know this is false. But again, they usually don't ask about the planar rule, so I wouldn't worry about it. Fully conjugated. Now, what does it mean to be fully conjugated? Fully conjugated means that every single member of the ring that you're looking at is either on a double bond, has a lone pair, or a charge. So for example, if I look at structure A first, this carbon's on a double bond, as this has a double bond, that one, that one, that one. Every single carbon of structure A is on a double bond and is therefore fully conjugated. And in an example like structure B, B is also fully conjugated because all 4 of these carbons have double bonds and this has a charge. So again, to be fully conjugated, every member of the ring must either be on a double bond, have a lone pair, or have a charge, positive or negative. Okay? So then what about E? Because E looks a little weird. The double bonds aren't in the ring, the double bond's sticking off. Does this count? Well, remember how nitrogen can resonate with this ring. This nitrogen has a lone pair that can swing down and resonate up to the oxygen, and so you get a resonance structure that looks like this, O minus, nitrogen double bond positive. So this puts the double bond in the ring, so this ring is still fully conjugated. Any others that follow? Nope. So that's the special thing about choice E. So every single one of these rings is in fact fully conjugated because every member either has something with a lone pair on it, a double bond, or a charge. So what it finally comes down to is the last rule, the 4n plus 2 rule. And all this means is that when you count all the electrons in your ring, are they a multiple of 4n plus 2? Meaning, if n is equal to 0, then 4 times 0 is 0 plus 2 is 2. So 2 would be a allowable number of electrons. And then 6, 10, 14, 18, so on and so forth. Any total number of electrons in the system that is equal to any of these numbers and then plus 4 forever, those will work. So let's start with A. First of all, how do we know what gives electrons? Double bonds give electrons, lone pairs give electrons, and negative charges give electrons. And each of those will give 2. So double bonds are worth 2 electrons, lone pairs are worth 2 electrons, and negative charges are worth 2 electrons. Okay? Positive charges are not worth any electrons. All they're used for is keeping a system conjugated. So you don't have to worry about that. So let's look at A and count how many electrons there are. 2, 4, 6, 8, 10, 12, 14. 14 is on my list of total electrons that make something aromatic. So A is in fact aromatic. That can't be my answer because we're looking for something that is not aromatic, meaning anti-aromatic or non-aromatic. B is fully conjugated, a ring, it's planar, and it has 2, 4, and then the negative charge is worth 2 as well, so 6 electrons. This is also aromatic, so that can't be my answer. Choice C is a 7-membered ring and a 5-membered ring on top of each other, but they're conjugated and in rings, so 2, 4, 6, 8, 10. 10 is on my list, so C works as an aromatic as well. Now D is a trick question of sorts because, well, how am I going to count this? I said that lone pairs and double bonds each count for 2. So I have 2, 4, 6 from the double bonds alone, and then does that also mean I have another 8, 10 from the lone pairs on the nitrogen? No, I don't. Because this is an important rule. If a member of the ring is already on a double bond, then if it has a lone pair, that lone pair is not counted. That lone pair is not going to resonate into the ring, so it's not part of the conjugation. So all you need to know is whenever you see a benzene ring, but some of the carbons are nitrogens, those nitrogen's lone pairs are not affecting the aromaticity. So in total, there are 2, 4, 6 electrons, and this is aromatic. Just as a side note, to give you another example though, is what if there was an oxygen in a ring like this? Let's add some room. You've seen that D is not the answer, so I'm going to erase that. What if I had a 5-membered ring where there's an oxygen here, and then 2 double bonds like this, and now oxygen has 2 lone pairs, and the question is this structure aromatic? Because now it's a matter of 2, 4, 6, 8. Is this aromatic or is it not? Because we see that 8 isn't on our list. Well, it kind of comes down to the same idea as before. Are both of these lone pairs resonating into the ring? No, only one of them is. If I want to show this oxygen resonating, I bring this down and then this double bond resonates to wherever it goes, but that would mean only one lone pair has been used, and I get something that looks like this. Double bond, not there. Double bond here, now it's O positive. Double bond here, and then eventually the negative will get pushed over there. And so now I have 2, 4, 6 electrons, and since this oxygen is on a double bond, that lone pair doesn't count. So this would still be worth 6 electrons total, and so this was an aromatic structure as I drew it out originally. So I had this originally, but through resonance, it became what I showed before, but it was still aromatic. So this structure is in fact aromatic. Now let's look at E. Based on that resonance I was talking about before between the nitrogen and the carbonyl, this is probably the structure you want to look at. And so I have 2, 4, 6, and you only count the electrons of things in the ring, so this oxygen has no effect, and this nitrogen is positive, so that has no effect. So it's 2, 4, 6 only, and that means it's aromatic because it's on our list. Finally, choice F. Well, that's the only one left that we haven't solved for, so that must be the answer, but why? So this nitrogen has a lone pair on it, this nitrogen has a lone pair on it, and now let's look. Every member of this ring is either on a double bond or has a lone pair, and so now I just need to count my total valence, or my total electrons, and I get 2, 4, 6, 8, 10, 12. 12 is not on this list. 12 is a multiple of 4. And if you ever have a structure that is a ring, is planar, is fully conjugated, but has a multiple of 4 in its total electron count, that structure is anti-aromatic. So choice F, aromatic, is an anti-aromatic structure, which means it's not aromatic, and therefore choice F is your answer.